this. So I said, now this is your quiz, so you don't need to write this down. You have an incident electric field. The value of the incident electric field is 30 volts, right, per meter. And this is going to hit, and there's going to be a reflected field, and there's going to be a transmitted field. And here, when we look at this, we take a look, we see that eta, I'll call this, since this is air and that's eta naught, I'll make this eta 1. The numbering makes no difference, everybody. You can call it eta 0, eta 1, eta 1, eta 2. You can call it eta A, eta B. Doesn't matter as long as you distinguish the regions. Everybody okay? I'm just trying to be clear about it. So eta 1 is the square root of pi, really, I'll do it this way, j omega mu over sigma plus j omega epsilon. Here, let me just say one other thing. The frequency on this one was 10 to the 6th hertz, right? Check your paper. Y'all follow me? Was it 1 megahertz or 10 to the 6th hertz class?
1 mega.
Huh?
1 mega.
Well, that's 10 to the 6th hertz, right? What I'm trying to tell you is when m, it means 10 to the 6th. Some people mistook that as 10 to the 9th, I think, or I'm not sure if it was 10 to the 3rd or 10 to the 9th. M is mega, it means 10 to the 6th, and you should know this. I'm not saying something here that's asking too much. I don't think I do. All right, so if that's the case, omega is 2 pi f. Now, I expect you to be able to do this seamlessly. I mean, you've done an F for a long time, right? F is not omega. All right, make sure you get this. I know I'm saying things that maybe seem insulting, but it's not meant to be. I'm just warning you that there are things that indicated that you thought that, or at least you made that mistake. Now, after that, now that I have omega, I'm not worried about the value. Here, I'm going to say that mu can be replaced with just mu 0. Do you agree? Because mu relative is 1 in that region class? All right, so just make this mu naught. Now, sigma will be 10 to the minus 3, right? 0.001, correct, class? Here, I can replace this with 3 times epsilon naught. I think some people got confused and they forgot that there's an epsilon relative here. I'm not absolutely certain about that, but because it was very hard for me to figure things out. But you all understand that's complex, right? Because of sigma value, right, class? Now you're going to get a value for this. I have the answers down, I think, for this one. Can you give me the magnitude and angle? Would you do this on your calculators? Because I have people literally write that down and I have a wrong answer. Have a magnitude at an angle of 0 degrees. This should be about 45. I think. You check it.
I had it at 40.26 degrees.
Anybody confirm that? And what's the magnitude?
88.25.
All right, that's what he got. Anybody else? I mean, do it on your calculus. There's mistakes here. I'm trying to just figure out what you guys did. And if it's a calculator error, figure it out now. I'm telling you that calculators these days make you feel very comfortable that they're so easy to operate, but there's errors that are creeping in here. I don't know what they are. Because when I see this, I mean, not this, but I mean, this equation, and I get something like 120 pi at an angle of 0 degrees, I scratch my head. I don't know what happened. Y'all follow me on this? Does everybody agree with this, first of all? Right? I mean, this is something we got to have down pat. You know, j omega mu over sigma plus j omega f. That should be, I mean, you got to know that's intrinsic impedance, period. All right? It defaults to 120 pi in free space, right? If it's a good conductor, the angle will go to 45 degrees and it'll be small. But nevertheless, what do you get? Did you guys confirm this, anybody? If you didn't get it, just tell me what you got. I think that's right, Jake. I don't remember it exactly, but I think that's right. Anybody else?
I gotta see where the errors are. Anybody get a different value? I suggest you put omega up by itself. So, I mean, maybe I better. You go ahead and do it your way. Your students, you know how to do this best. You got that?
Yeah.
I got 2 people got it. No?
I think I made a calculation error.
I think a lot of people made a calculation error. You're not alone. This is what I'm trying to figure out. Please make sure you figure out where the error was. And this should be honestly just seamless. Follow me, guys? Now, if you got a real and imaginary part, that's what I put in the solutions. I think I put the eta as real and imaginary. If you look in that on one line. I felt bad about this, by the way. I thought the grades would be 9s and 10s the whole way, and I didn't know what happened. Nothing? No? Did you get this? You got it? How many got that? Let's try that. 1, 2, 3. Did you get it? No? If you're not doing it, I understand, but I'm asking you to do it because lots of people, did you get it right?
I'm sorry.
All right. I'm assuming you can do this fairly quickly. Maybe that's a bad assumption because this, if you're plugging in U naught, epsilon naught, I can see how that could be time consuming. But if you got those in memory, and I don't know how easy it is to do. I thought it was easy to designate something in memory and pull it back. I don't know if you could put a symbol next to it to identify, but anything that would help you get this through, because this shouldn't be hard. I got 3 in my class that got it. Still working on Ashley?
I'm just converting to degrees.
Well, you don't have to. Did you get the same magnitude?
I didn't. I was trying to convert to degrees to verify.
It doesn't have to be degrees. I'm worried about the magnitude. If the magnitude's right, the angle has to be. No? All right. Now, that's the right answer, I think. I'm just asking you, please make sure in your calculators, these calculations aren't overwhelming. They should be automatic, really. It's not a hard calculation. It's not meant to. You okay with this, everyone? How many got it now? You didn't get it, or did you?
Yeah, I thought I was putting it in right. I don't know.
What kind of calculator?
Sir?
Calculator? What kind?
TI-84.
Anybody got an 84 in here? Usually I can call and somebody will have it and they can show you if they know how to do it, but I don't know. Could you please make sure you can do this, everyone? I'm going to move on. All right? So this is what eta 1 is. This is the big deal. This is where probably 80% of mistakes are right here. I mean, maybe it's not quite that high, but a lot of people couldn't get this right, even with this. Right? That concerns me. Now, if you have that, so we've got the incident electric field. This is the way I like to look. You write down here, you got incident electric field's the first thing given, right? Now the next thing you want the reflection coefficient. This is going to be a complex number. Just write it down like this and it helps you. You have eta 2 minus eta 1. Or really, in my case, I have eta 1 minus eta naught, right? The order is important. If you don't do the order right, you get a negative value for the reflection coefficient. And I think people made that mistake. Actually, it's easy to do if you're not attentive. Right? You take the impedance you're going into minus the impedance you're coming from. Now for this one, what do you get? Well, you got the values for eta, right? Eta 1 and eta 2. It's complex, isn't it, class? So what I would do is store eta 1 in memory. If I was you, I'm just telling you this. Then I'd recall it, subtract 120 pi from it, either store that, or then divide that quantity by the quantity eta 1 plus eta 2. It will be a complex number. It has a magnitude and angle. Y'all follow me? Give that to me in terms of magnitude and angle, please. And please use your calculators when I'm doing this. I'm doing this for your benefit, not mine. I'm trying to encourage you. Do you have calculators or not? If can you get them out, guys, and just try this? If you don't want to, I can't make you, but I'm trying to make sure. This is one of these desperate times for me because my assumptions are being crushed. I assumed everybody knows how to use their calculator very well. But if you got a new calculator for Christmas or something like this, then there goes my assumptions.
I got it right. I forgot the square root last time.
What's that?
I got it right. I just forgot the square root last time.
Well, it's easy to do, and sometimes, well, my biggest problem is the cosine in a lot of calculators. Because cosine defaults in some cases to degrees. You have to make sure if you're going to take a cosine, if you're going to do something with cosines, you have to know if it's degrees or radians. Now, not this problem particular, but others, okay? And we're going to see what the power equation becomes for. What did you get, Jake? You seem to be.
Let me add one to it, because I accidentally got the,
No, this is reflection.
or I meant I accidentally got the trans,
Well, then,
the other code.
wait. If it's the then you need to subtract one and change the sign. It's one, what he's saying, here's the relationship. 1 plus the reflection coefficient is the transmission. He's saying got transmission, and he wants reflection, so you have transmission minus 1 with a minus sign, or 1 minus transmission is reflection. Y'all follow me? What'd you get?
0.7028 at an angle of 162.25 degrees.
Anybody confirm that? You got that? Anybody else? You got it? I'm assuming that's right. Make sure you can get this, and please make sure you practice this problem with even different values so it's second nature. It should not in any way, shape, or form cause you any kind of duress. Now I've got that. I've got reflection transmission coefficient is equal to 1 plus reflection, or it's equal to 2 eta 1 over eta 1 plus eta 2. Either of these formulas will get you it. Some use this, some use that. I can't tell you the percentage. It doesn't matter. There's 2 ways to get most of these answers, 2 or 3. So what do you get for transmission? But again, it hinges on getting the impedances right. And that's always an assumption. I assume you have this. Did you get it? You're just adding 1 to the reflection. Add 1 to this number.
I got a 0.39399 at an angle of 32.95 degrees.
And then go say that again.
32.95 degrees.
Okay? Y'all with me? Now here's the thing I do. Just because there's enough here to cause you some mistakes with either your fingers or something like this, automatically I'm going to see if I take the reflection coefficient and I take the transmission coefficient, if I take the reflection coefficient, if I take the transmission coefficient minus the reflection coefficient, I should get 1. So I'll simply take tau minus the reflection coefficient. I better get 1. If I don't get that, I've done something wrong. You follow me? This is just a check. It doesn't take but a second. Y'all get that? Mathematically, you have to if you've done the other 2 things right, don't you? You're going to get 99.99 something, but it's very
There's
close.
rounding error, but it's, the angle is at like 2 to the negative 12. Or
Yeah, don't worry about it. That's 1. So you checked it, right? Now, after you get the electric field, after you get these things right, now I'm going to get transmitted and reflected E field. So now I've got the transmitted E field, or I'm going to get reflected. Reflected E field is just reflection coefficient times E incident. That's going to be complex. I put it here, and then I get the transmitted E field. And that's transmission coefficient times E incident. Those are both complex, right? And again, I only cared about the magnitude. If you got the magnitude right, the angle had to be right. Can you give that to me? If you don't mind. They're on OneNote, but I'm just asking you to do them. I guess what I'm trying to do is force you to use your calculators. That's really my goal here. Just because of some concerns I have. Who got a new calculator over Christmas?
I got 11.82 to the 32.
Reflected?
Oh no, I'm sorry. Initial. Or no, yeah, transmitted. Yeah, that's
What
what I
is
did. 11.82 to the degree of 32.9. But I could be wrong. Let me see.
I'll second you on that one, and for reflected, I got 21.0859 at an angle of 162.246.
What?
246.
I got both those answers.
All right. Now, if you look in OneNote, I put them in real and imaginary. So in case you got an odd angle, you could break it down that way if you put on OneNote. All right. Y'all with me on this class? And the reason is if I take this, right, I can put a negative sign here and add 180 degrees to that. It's still the same thing. I can add or subtract 360 to 162. It's still the same point. And sometimes your calculators default to different angles. Sometimes, I don't know nowadays if it happens, you get a different sign here, different angle. They still are identically the same. With me? Now that I have that, the next thing I'm going to get is going to be the transmitted and reflected power. Most of you by this time get the idea, but there's a lot of mistakes in what I'm about to show you. So now when I talk about the transmitted power, I'm going to say that's 1/2 the magnitude of E transmitted squared over the magnitude of eta 1, but it's also going to be cosine of the angle of eta 1. Are you with me on this, everyone? Yes, sir.
When do we know when to use the cosine and when not to use the cosine?
This is a power function. You have to right here if it's lossy, right? If it's lost, well, you can use this all the time, but here's what I'm going to say. If it's lossless, right? Let me just take you over here, because this is a good time to get all this stuff out of the way. When I look at the general formula for eta, it's square root of j omega mu over sigma plus j omega epsilon. Do you agree with that? Now that is got, in general, a magnitude and an angle, correct? The angle will always be between 0 and 45 degrees. It'll never be more than that. I can assure you, if it is very, very lossy and sigma dominates, then the square root of j is 1 at an angle of 45. I know the greatest angle possible is 45, and the minimum angle is 0. If it is lossless, like such, then the j omegas cancel, and I get square root of mu over epsilon. You all see that? So then you have just a real number at an angle of 0. So when you see an intrinsic impedance given at an angle of 0 or strict real, you know it's lossless. Got it? Some of the homework problems I gave you bring that out. You should have, let that set in your mind. A lot of the homework problems I try to give you, if you do them, you say, oh yeah, it has to be that way because I know alpha is 0, it's lossless because the impedance is strictly real. Got me? Now, getting back to and you can always use that, right? Always use that. And this is transmitted power. It's not power as a function of distance, though. It's just on the other side of the border. You can always use that. Now, for reflected power, P reflected, it's same formula. Magnitude of E reflected squared, and here it's going to be over eta 0. You could put down the cosine of the angle, but we know it's 1, right? Cosine of 0 is 1. Agreed? Now, I think we're all aware that reflected power is going in the opposite direction as transmitted power. So I don't make it a point to ask you for a negative value there. Because when it's reflected, it means it's going the other way. It's sort of a necessary implication. Got me on that, everyone? And another thing with dB, a dB is a positive coin. We say dB of attenuation, it's positive. Technically, the field's going down. So if you take 20 times the log as the field of it's going down, you get a negative value if you normalize it to the incident field. But it's always going to be a positive value for dB. Do you all follow me on that? dB of attenuation. Now, dB gain, it assumes positive. Are we all good on that? Did you? Oh, we didn't get these values, I'm sorry. What did you get for transmitted power? I didn't even put down incident power. How about P incident? P incident would be 1/2 magnitude of the incident field, 30 squared, divided by 120 pi, right? You can tell me, I forgot exactly what that was. I want to say it's 1.19?
Yeah.
Is that right? Check that, see if you get this. This is 1.19 watts per meter squared. I didn't care about units here. Dr. Gross would yell at me. But it's an implied unit. If it's power density, if you got an electric field, you can only have power density. It can't be power in watts. It's not a value of power for a single resistor or something. What's this one going to be? Two ways to do this. You could take E transmitted. What you could do is, here, you could take E reflected and just put reflection coefficient times E incident. And then you could take 1/2 E incident squared over 8 or the incident power times magnitude of the reflection coefficient squared. You could do it that way, but you can do this a lot of ways. This is the way I'd set it up though. How about for P trans or P reflected, anybody?
For P transmitted, I got 0.604.
I think that's right. Anybody? That's watts per meter squared, but anybody want to confirm that? You got that? Anybody else? Try it on your calculators. You'd be surprised. This right here is where I concern myself, because it's implied that the angle is stored correctly. If the angle is in radians, you got to do the cosine in radians. If the angle is in degrees, you got to do cosine degrees. You can't mess that up, and I'm not sure if that happens. Did you guys get it right in the back? You got it?
I got it.
Try it again. If you didn't get it, try it again. Did you get that right? Or not? You did? Good. All right. I'll be quiet. What about this one?
I got 0.589.
0.589 watts per meter squared, right? Anybody else get that? Good. While you're doing it, got a question for the audience. How else could I get the transmitted power without going through this calculation?
Oh, you could do,
Isn't the real parts?
How about taking the incident power density minus the reflected power density? Isn't that the transmitted power density?
Mhm.
Now you can do that as a check. This is quick, because the reflected and incident power, there's no cosine of funny business. Do you follow me? The only complicated calculation you have is for the reflection coefficient. This will get that, right? You with me? So that would be the transmitted power. Not only that, from that, believe it or not, no, I'm going to leave it alone. I'm going to go through. Are we good on this one, class? Now, if I gave you another quiz with the same information required, do you think you could do good? I may just do that. Hint, I may just do that. Either tomorrow either Wednesday or Friday, just to confirm my suspicions that I've got great students, not just average students, students with ears to hear what the professor says. I'm trying my best. Huh? We good on this? What I'd like to do now is move into oblique incidence. We did the shielding without really going through any elaborate schemes, but for shielding, the whole deal is what we're doing here is getting the impedances right. You go from air shielding, right? And then to air, and to get the shielding effectiveness, transmitted electric field, right? And we're going to do thick shields. I'm just telling you. I don't do thin stuff. That's sort of irritating, and nobody uses thin shields. The only time you're really doing that is when shielding is there, but you want to see if it's effective enough. Then you got a thin shield problem. Like if you get a real thin chassis of aluminum and you got it over a device, you want to see if that's good enough to shield you from incident electromagnetic energy at a certain frequency. Then you find the shielding effectiveness, and you use the entire equation. But generally speaking, when you design a shield, you make sure it's thick enough so it kills everything, basically. All right? But you can use the approximation. Any other questions about this before I move on? All right. We did shielding, or we did really three, I should say slab problems with three different materials, technically only two different materials. We had air, a shield, and air was normal incidence. Now what we're going to do is go through oblique incidence, and this one I will give you the formulas. I'll give you the formulas and from this, and we'll also prove Brewster's angle. I'm erasing. Is there any information about COVID or anything happening that you guys as students know that I don't as a faculty member? Like any places closed downtown, any places are having specials on food or anything like that? I'm asking this because my other class used to be a wealth of information. They could tell me where to get cheap stuff, cheap masks and stuff like that. And hey. As a matter of fact, I have not had COVID. I've had both a nasal swab and a test when I was sick the other week. And they said, basically, you don't have it, you had something, at least you didn't register. If you ever feel sick, please do not come to class and go, if you can't get over here, because I tried calling that place myself several times, I never could get anybody to respond to get an appointment to get tested. You can go over to those urgent care centers. You can go to them, they'll do it, and insurance pays for it. If you're at the university telling your student paid for, you can get a fairly rapid test, 95% accurate. And if you're very suspicious, pre-existing conditions, you can ask them, they'll send it off for 99% accurate test. They'll take, I think it's another nasal swab. And if you think you had it and you want to see if you did, you can get antibodies, and they send it off. So what I'm trying to tell you is, and we're being encouraged to do this, if in any way, shape, or form you feel sick in any way, cold, flu, anything like that, stay home. Just let me know that you're not feeling well, and go get yourself tested, and I'll keep you up to date, okay? All right, so oblique incident. Oh, yeah. What I'm doing, this is on page, there's two types, PE and PM, and I want to go through this. I'll tell you one thing about this. It gets a little irritating. I think I gave you the reading. It starts on page 359. Didn't I, class? In the homework. If you do it, please do it. Don't get behind. Read it. This is important, and here's why. There's things that are called the Brewster angle, where you get perfect transmission of the electric field, no reflection at all, for a TM polarization. And there's also something on the horizon for all of us. Have you heard of metamaterials, anybody? Have you heard the term cloaking ever? Have you ever seen the movie Predator? Have you seen how that beast is like shimmering? All right, what happens is with cloaking, well, first with radar absorbing materials, all this angular stuff becomes very important that we're going to do here and study. But with radar absorbing materials, a wave hits and doesn't reflect back theoretically. That's not true. A very small wave reflects. That's one thing. Or the wave is redirected somewhere else, not back at the radar where they can pick it up. There's another thing called cloaking. This is advanced stuff. And probably if they've got anything working, I'll never know about it because it'll be too classified. Cloaking is this. Assume you got a sphere here. Electromagnetic waves coming here. The wave will hit the surface, then run around, and come out at the point it would have naturally come out of if it was unimpeded. The problem is there'll be a slight phase change when it does. So if you're on this other side and you're looking at something that's cloaked, you'll see it like shimmer. Now, they've done it with theoretical modeling. I think they've done it with some things, but it has to be at this time, normally incident energy has to be at one and only one frequency, and it requires something called an artificial dielectric. It's double negative. You're going to see what that means in a second. Generalized radar absorbing materials in true cloaking requires that for any angle of incidence, very little of that wave is either reflected or all of it's transmitted through as if the thing isn't here. Now, really, the truth is this. Whenever I hear of a lot of UFO sightings, this is me, because I was there when the first stealth fighters were flying all over the place, and people swear it was a UFO, even though radar had nothing. I'm not kidding about this. I was in 1989, 90, 88, 89, and 90. I was up in Huntsville, 2 at NASA, 2 fellowships at NASA, 1 working for the Arsenal. The Arsenal stuff had to do with hardening multiple launch rocket systems to lightning vulnerabilities. In that, does anybody live in Huntsville? Ask your parents if they got remember anything about both tornadoes in 89 and UFOs in 88 and 89. That was the stealth fighter, the F-117 fighter bomb. It's called Blackbird. You know, I mean, not Blackbird. Oh, I'm trying to think of the name of it. But do y'all know what I'm talking about? The only reason I know that exists is because of the first Iraq War. Right? We would still not know it exists. But I'm hearing all these UFO studies. Has anybody else seen this stuff on the internet? And I think, sounds like the old days. That said, this stuff is directly related to it. So if you're an X-Files person, if you know what that is, or you like spooky stuff, you're going to love this. Because we're going to get into a couple things that happen. So let's call this region 1, and it has Eta 1, Beta 1 here. Let's call this region 2, Eta 2, Beta 2. And now we're going to talk about these 2 regions. It's still going to be a plane wave, but now it's not normally incidence. So what we do is draw a normal to these regions. This is like, I don't know, you can call this polystyrene, you can call it what you will. It's something different than this. Call this air. Doesn't have to be air, but it's good to start there. Now, our first case we're going to do is called transverse electric, or TE. This is in the book. The symbol is TE, and normally you'll see the E field represented as TE either down here with the superscript. So that tells you it's the transverse electric. So what is transverse electric? Let me tell you. We're going to assume a wave is coming in at an angle, and the electric field is coming out of the board, and the magnetic field will be into the board. So the electric field's coming out. This incident electric field will have a value, if that is Z, and in his book, I want to stay consistent with his coordinate system so I don't lose you. He uses X up and Y out of the board. So this is X cross, so Y's out of the board. And this E field will have a magnitude of E naught incident. It'll be E to the minus J beta 1 times Z hat. And call that Z1 hat. And it will be in the AY direction. How many have your book here? If you have your book and you look at page 360 and 361, you'll see the drawing I'm trying to refer to. So this is the E field. Now, here's what TE really means. This will get through to you. You see there's a wave coming in, and I should put, this will be the angle of incidence. There will be a reflected wave here. It'll still be TE polarized. And the H field is this way. Here the H field has to be in this direction. That'll be H reflected. This will be E reflected. And here E reflected will be equal to some E naught reflected times E to the J beta 1. And what will happen is that that's Z1 prime, or I'll call it Z incident. This will be Z reflected. It will be in the AY direction. And the H field's coming this way. I didn't put the equations down yet. And then here we're going to get a transmitted E field.
and the transmitted E field is coming out of the board. The H field will be like this, and the E field transmitted will be some E naught transmitted, e to the minus j. This will be B2, and call this Z hat transmitted. Now I'm just setting this problem up. So we have an H field and an E field in either case. And if you look at the incident wave, you got theta incident. Here is going to be a theta reflected. I'll tell you that the reflected and the incident angle are the same thing. And here, you're going to have a transmitted angle. And again, these are plane waves coming in at this angle. Now, if you think about fresh water, you could say it's got air and then you got water, and you want to look how the wave refracts or what the angle is here, all right? Everybody with me on this? So when we do this, normally what we do, I'm going to say what Z incident is here. So Z incident, and I did this last time, Z hat incident would be equal to the cosine. Actually, let me put the sine first and put X first. It would be cosine, sine of theta incident, then it's going to be X plus cosine theta incident, and then Z. Now this is in the book, and I drew that triangle last time, if you recall. You all remember that? All right. So this is Z prime is really this axis, that's Z incident. When I take a look at Z reflected, superscript below, Z reflected will be equal to, let's say you have the same X coordinate, but it'll be sine theta reflected, and it will be X, but it will be minus cosine theta reflected Z, and I'll explain that in a second. So this is theta reflected. And then when we talk about Z transmitted, right there, that will be sine of theta transmitted X plus cosine of theta transmitted times Z. Now, just for a second, I'm going to do this. If you remember, the way it worked is, I said, if we have this as Z and this is X, and we talk about this, and actually, the way I'm doing it, I've got this upside down, it should be this way. If we take a look at this Z, this X, then this would be the incident angle, right? Draw perpendicular. This distance, if you take a look at this, it would be adjacent over hypotenuse, so this would be cosine of the angle. This would be Z cosine of the angle. If you look at this right here, this distance, that, since this angle would be this angle, that's going to be opposite over hypotenuse, would be the sine, so this is going to be X times the sine of the angle. And you can see how these things add up to equal, in fact, the distance in the Z prime axis. Do y'all see that, class? It's really just, you're going to get this length is Z cosine, this length is X sine, this is the Z prime axis, and that's this equation right here. So that's the incident. Now the difference with the reflected is this. This wave is moving this way. Y'all follow me? It's going positive X, positive Z. The reflective wave is still going positive X. Do you follow me? But it's going negative Z, and thus this sign change. You'll have to work with this to fully appreciate this. Now this one is still going positive Z, positive X, if you take a look. And again, I set this up to do so because I assume the wave is coming in like this. somewhere between 0 and 90 degrees. Do y'all follow me in this class? If I was measuring the angle up here, it would be different, but this is the way I'm setting it up. Now, when I do this, I have to have unit vectors in each of these directions. You with me? So the unit, that's a little fast. So the unit vector here, the propagation vector actually for this, the incident wave, would be equal to simply sine theta incident AX plus cosine theta incident times AZ. Same down here, the propagation vector, and this would be for transmitted, would be equal to the sine of theta transmitted AX plus cosine of theta transmitted AZ. This is the different one. The reflected angle, unit vector in the direction of reflection, would be equal to the sine of theta reflected AX, but it would be minus cosine of theta reflected AZ. Okay, those are the unit vectors. You can do this yourself and find them if you want by taking, once we get the power, you simply take the power, E cross H, and divide by the magnitude of the power. That'll give you a unit vector in the direction of, and you'll see this in fact works, okay? I want to leave it at that for now. Now, once we have these things, first thing we're going to do is get the H field transmitted, all right? Or I mean, the H field incident. We'll get the reflection and transmission coefficient. Now, if we want the H field in general, this is the go-to equation for plane waves. So write it down in your notes, like star it and say, Baginski said, this is important, this is the one. This is the one. The way we get the H field, in general, is taking 1 over eta. You can mark this down at loss and stuff. We're not going to cover lossy oblique incidents because it gets a little too complicated for undergrads. It's a natural progression, but the problem is the mathematics for the power gets a little much when you take E cross H conjugate. It gets a little burdensome. It's still 1 over the 1 over eta. Then it's going to be a unit vector in the direction of propagation across D. Now that's the general form you always go to. This assumes steady state. It assumes a plane wave. You can write that down plane wave, but all the assumptions on here plane waves. When we do that, then we find that the H field incident would be equal to, first I take 1 over eta 1, right? Whatever that is, unit vector in the direction of propagation, that's this. So I'm going to have sine of theta incident AX plus cosine of theta incident AZ. And this is crossed with E naught incident over, I'm sorry, E naught incident, that's a naught. That's an I. E to the minus j beta 1, I'm going to just call it Z1 prime, or Z1 incident, and the AY direction. Now, you all follow me what I've done here. I didn't put in what Z incident is because it gets a little long. It's just an argument of the exponent here. I just put in the AY. That's important. I want to make sure, if I don't go any further today, I want to make sure I get this out. Are we good on this? Now, follow me when we do this. In this, you'll see how the progression works. So that means H incident still have a value of 1 over eta and E naught incident. So I always break that out in front. I call this E naught incident over eta 1. You'll notice I'm assuming lossless, so don't worry about that angle. I can add it. It only gets, the complications get severe here. Well, to me, severe. Now, next thing I'm going to do is take AX crossed AY. What is that, guys? X crossed Y is? Z, right? Y'all with me? So it's AZ. So I have sine of theta incident AZ. Now follow me on this. Z crossed Y, guys? Minus, right? Minus cosine theta incident And it would be zy ax, right? And this whole thing is times e to the minus j beta 1 z1 prime. And you leave it like that. Now you'll notice what I've done. I just left the z1 here. His book doesn't. Do y'all agree with that? That's the incident. Right now, if you have to go, you can go. Technically, my time is up. But if you want me to hang out, consider this an office hour. How many have classes right after this? You do. Where is your class?
At work,
You got work where?
BK,
How long does it take you to get there?
a couple minutes.
Okay. This is my office hour for you. But if you want to go longer after this, I will if you have questions. Let me just finish this if I can. But if you have to go. It'll be recorded thanks to Jake here.
William.
William.
No, you're fine.
I'm sorry. I've been messing this up lately. I've got my classes recorded and my Zoom meetings recorded. I'm messing up everything. Anyway, we got this, right, William?
Yeah.
Anyway, now how do we get reflect or transmitted field? I want you to just take a look at this for a second so we can make some analogies and assumptions. Y'all see how this transmitted vector has the exact form as the incident vector, except the angles are different, right? Y'all see that? And when you take another look, if the transmitted electric field, they're all sticking out of the board, they're all TE, right? I don't know if I got this, said this as well as I should. When I say TE mode, that means the electric field is perpendicular to the plane it's traveling in, but here's the real way you tell. Listen to this, forget about what's in Dr. Wimmer's book. You see how this is a region right here, it's an interface? That's like a flat wall coming out of the board. The E field is in that plane, it projects right into it. It would be like if I had an E field propagating into this board, right? Let's say the E field was propagating, if you can imagine this way, but the E field's sticking out like this. That would be TE, y'all follow me? Now, if the E field's still a wave propagating this way, if I had the E field like this, and the H field, where the H field is going to be parallel to the board, that would be TM because the H field is sticking out of the plane, it's propagating it, and it's also parallel to the interface, or in the plane of the interface of the two media, the entirety of the vector. So that would be TM. It's transverse magnetic and transverse electric. Getting back to this thing, based on that argument, I can take this equation, turn this into transmitted, this into eta 2, this into sine theta transmitted, this into cosine transmitted, this into beta 2, and this into z transmitted. Do y'all follow me? So doing so, now I get E naught transmitted over eta 2. Now I'm going to have the sine of theta transmitted, AZ, minus cosine of theta transmitted, AX, e to the minus j beta 2. And what's my z goes here? Which z?
Z.
Z, say it?
T.
Z transmitted, right? Right there. And I'm just going to put ZT here. You don't have to put a hat on yours, but I do mine. Now, here's the deal. When we take a look at the reflected field, it's still 1 over eta 1, unit vector in the direction of propagation of reflection crossed into E reflection. I'm going to make a case here. I just want you to think about this. Eta here is the same as eta here, right? Same as the first, it's in media 1, right? Beta is the same for this E field. Do you all agree with that? The one thing that is different, there's no reflection coefficient here, is that the direction of propagation has the same sine theta, right? Reflected AX, but the Z component's got a negative sign. Do you all see that? That means one thing. You see how there's a negative here? It'll become positive. You can take a look at Wentworth's book. That's the only thing. And you can take a look at his book and confirm what I'm saying. So this one becomes E naught reflected over eta 1, right? And then there's going to be sine of theta, you don't have to memorize this,
in the AZ direction, but now it's positive cosine of theta reflected AX, not negative, and it would be e to the minus j beta 1, and now it's z reflected at. And that's the three H fields for the different regions. Now here's what I want you to just listen to me. I'm not going to do it right now, unless you really want me to. But if you got to go to work, I don't want to get a letter from your boss. Because I know, I mean, people have commitments. Athletes are the worst. If you're on the football or basketball team and you got to make bus, if you're not out of here at a certain time, they'll send people over here to drag you out. And I've not had that happen, but I know all about athletics. And I don't, is there any athletes in here? I said, I'm assuming there's not, but thank God. All right, now back to this thing. Here's what they do. They're going to take the tangent E fields on one side equal to the tangent E fields on the other. You'll notice that all the E fields are tangent. Incident plus reflected on this side equal transmitted, right? So the only thing we do, and I'm going to go ahead and do it right here. You can go, guys, if you want, but I'm just going to tell you. The first equation that we use is E naught incident plus E naught transient, or reflected, pardon me. Reflected is equal to E naught transmitted. You'll notice here, we're going to evaluate them, by the way. I'm going to say this at z equals 0. And when we evaluated z equals 0, all these exponents go to 1. Y'all see that? With me? All right, so this would be the first equation. That was the first equation last time when we got the normal incident case. And all the things I show you have to default to the normal incident case for reflection transmission if the angle is 0. Y'all with me? That is normal incident. And the second thing we do is H tan 1 is H tan 2. Now please listen to this. This is important. So when we look at this, here's the H field in all cases, right? Which one of these is tangent and which component is not tangent? Well, tangent has to be either in the X or Y direction, correct? The E field was in the Y, it means the X component of the H field is tangent. Do y'all follow me on this? There is a Z component, take a look. If you're here, the E field's out of the board, but the H field is in this direction, correct? And if you want to know the direction of propagation, E cross H is that way, right, on your right hand? It works. So the H field component I'm looking for would be in the X direction. So what I'm going to do now, a different color, I can just circle what I'm going to use for the tangent component. I'm going to take, I want the X component, right? Right? Everybody? So I'm going to circle this and this, this and this. Notice the negative sign. And this and this. These are the tangent H field, right? We're going to let z equal 0, and we're going to equate it. And I'm going to say H incident, which is this, plus H reflected, which is this, is equal to H transmitted. With me? And then I solve for the transmission and the reflection coefficient as I did before. I'm already holding you. If Mark Nelson comes down, he'll chastise me for this. And here's what the real bottom deal is. I'm going to put this on one note. What you're going to get for the TE polarization, now Wentworth doesn't do it. I don't know why he doesn't show this standoffish, but he doesn't show you. I'm looking for that reflection coefficient. Where is it? What I don't like about this is he doesn't bring this, just break this thing out.